Have you ever paused, maybe on a train platform, and thought about what truly keeps our modern trains running safely, especially at those incredible speeds?
Yeah. Or, what protects them from just random glitches,
Yeah.
or even worse, someone trying to mess with the system deliberately.
Exactly. It's something most of us probably just take for granted. But the complexity underneath and the sheer brain power needed to keep it all safe, that's really something else.
Hmm.
So today, we're taking a deep dive into this incredibly sophisticated world. We're looking at train control systems and, crucially, how we actually assure their safety and security.
Right. And our mission here really is to unpack that complex engineering for you and the strategic thinking behind it all. How do we keep millions of passengers, tons of freight, moving reliably day in, day out?
And we'll explore how the experts actually spot potential dangers, often long before they could ever become real problems, using some pretty cutting-edge methods.
Yeah, this whole area is built on some fascinating research and a lot of practical, real-world insights. We're hoping to give you a bit of a shortcut to understanding what's happening at the forefront.
Okay, let's dive in. The first thing to grasp is just how much the landscape of train control has shifted. It's huge.
Oh, absolutely. We've moved on from, let's say, the older ways, more deterministic, hardwired relay logic.
You mean like actual physical switches, big levers, that kind of thing?
Exactly that. Big, clunky, but you knew what they did. Now, we're talking highly advanced computers, complex software, communication technologies everywhere. It's not just an update, it's a fundamental change.
And this shift, well, it introduces a whole new class of potential issues, doesn't it? Things you maybe didn't worry about with simple relays.
That's the core of it. Tiny, unforeseen interactions, maybe between just a few lines of code, could potentially cause big problems. These modern systems have countless supervisory and control functions, all tangled together.
Intricate interdependencies, you mean?
Precisely. And this sheer complexity makes ensuring the whole system is resilient, that it's safe, well, it's a massive headache for the designers, a real challenge.
So with this new complexity, this sort of intricate puzzle, how do you even start tackling potential problems? These undesirable states or hazards? Is it just waiting for something to break?
Oh, definitely not.
Yeah.
It absolutely has to be proactive, fundamentally proactive.
Yeah.
You need systematic ways to search for and identify those potential problems, the hazards, right at the beginning.
Earliest phases of the life cycle.
As early as possible. It's not just about saving costs later, although it does that massively. It's really about designing out the danger before it's even built.
Okay, proactive makes sense. But surely we have ways to find hazards already. Haven't we been doing this for years?
We have, yes. But some traditional methods, well, they have their limits, especially with these computer-based systems.
Like, what kind of methods are we talking about?
Well, take something like HAZOP, the Hazard and Operability Study, keep from process industries, like chemical plants. Great for that context.
But not quite right for complex train software. Why is that?
The main issue is that HAZOP often relies heavily on text-based specifications, written documents describing the design.
And the problem there is?
Natural language. It can be ambiguous. Different people might interpret the same sentence slightly differently. Plus, it's really hard to capture the true, intricate design intent of complex software purely in words.
Okay, so you might miss things. Overlook subtle interactions.
Exactly. You might overlook critical issues hidden in how the software components actually interact. That's where we see this big leap forward with the model-based approach.
Model-based, so using actual models like blueprints, but dynamic.
Kind of, yes. Using formal models drastically improves your ability to describe the design intent clearly. It's like moving from prose to a precise, shared engineering language. And it really helps with traceability.
Traceability? You mean linking a problem back to its cause?
Precisely. You can link a potential hazard directly back to a specific part of the system model, like having a map that shows exactly where the danger might lie.
Okay, that sounds powerful. How does it work in practice? Are we talking about one giant model?
Not usually. The power often comes from combining different types of models, different perspectives giving you a fuller picture.
Right, like looking at something from multiple angles.
Exactly. So you might have reference models or REMs. Think of these as the system's skeleton.
What parts connect to what?
Yeah, the main components, the subsystems, and how they're physically linked up. Then you have state transition models, or STMs. These describe the system's overall states or moods.
Like power on,
Yeah.
normal running, emergency stop.
Precisely. And how the system moves between those states, it maps out its entire operational life, if you like.
Okay, skeleton and moods. What else?
Then you've got functional hierarchical models, FHMs. These are like peeling back the layer.
In and into the details.
Right. They break down what specific components do, how a big function is achieved by lots of smaller specific tasks.
Yeah.
See the internal logic.
Okay. And the last one?
Sequence models, or SEMs. These are like the system's choreography.
How things happen in order.
Yes. How different subsystems work together, step by step, to achieve something in a particular state. They show the interactions, the flow of information commands, data, status updates.
Wow, okay. So REMs for structure, STMs for states, FHMs for function breakdown, and SEMs for the sequence of actions. That's quite a lot of models.
It is.
Yeah.
And you've hit on a potential issue right there. Using multiple models, well, can create new problems if you're not careful.
How so? Like them not matching up?
Exactly. They could be isolated, maybe even contradict each other. Or one model might be missing something that's shown in another. Incompleteness, that's the risk if they aren't properly synchronized.
So you need a way to tie them all together and make sure they agree.
Precisely. And the solution is something called intermodel constraints. Think of them as rules or maybe traffic cops for the models.
Okay.
They connect the different model types. So a rule might link the reference model to the functional model or the state model to the sequence model. They enforce consistency.
Making sure everything lines up across all the different views.
Yes. It ensures the whole representation is sound, consistent, and you don't have these isolated bits of information that might conflict.
Can you give us an example? Where has this actually been used?
Absolutely. A really good case study is the Chinese train control system Level 3 CTCS3. It's used on their high-speed railways.
High-speed rail. Okay, that's definitely complex.
Hugely complex. Massive scale, built by multiple different suppliers across a vast network. It's exactly the kind of system where you need these advanced methods.
So multiple suppliers. That sounds like a coordination nightmare. How do you ensure everyone's models are consistent?
Well, that's precisely where this model-based approach really showed its value for CTCS3's safety assurance. They build detailed REMs, STMs showing normal states, but also abnormal ones like fail-C3 FHMs for critical bits like the core processing unit, and SEMs showing specific operations like imposing a temporary speed restriction.
Okay, so they built all these models. Then what?
Then came the crucial steps. First, constraint checking. Rigorously checking for inconsistencies. Does this component exist in all the relevant models? Does this function have a corresponding state? Finding those mismatches.
Right, cleaning things up.
Then, hazard identification. They use specific guide words, prompts, applied to the models to systematically generate potential abnormal scenarios. What if this signal is lost? What if this component fails?
Trying to break it, basically, in a structured way.
In a very structured way. And finally, traceability checking. Linking every hazard they found back to specific elements in the models. This helps understand the root cause, prevents identifying the same hazard multiple times in different ways, and builds confidence.
Builds confidence in the whole system, piece by piece. Okay, so models help us handle complexity and prevent unintended failures. But what about intentional problems? Malicious attacks.
Ah, yes. That brings us to a really vital distinction, safety versus security.
They sound similar, often used together, but they're different beasts, right?
Fundamentally different. Think of safety as freedom from unacceptable harm, mainly from unintended things. Accidents, design flaws, maybe human error, equipment failing.
Okay, the traditional focus.
Exactly. Security, on the other hand, is about freedom from unacceptable harm or damage resulting from malicious intent.
Like cyber attacks. Sabotage. Someone trying to cause harm deliberately.
Precisely. And while safety's been the focus for ages, all this computing and communication tech, well, it opens up whole new vulnerabilities. Security needs just as much attention now, maybe even more in some areas.
So this changes how we even look for hazards, doesn't it? We can't just wait for accidents to happen and learn from them.
No, that's far too reactive.
Yeah.
And limited. We have to shift towards systematic, proactive prediction and prevention. And this involves, broadly, two phases.
Two phases.
Yeah. First, the empirical phase. This is where you use all the knowledge you've gathered from the past. Checklists, known failure modes, techniques like FMECA, failure mode, and effects analysis. Identifying known bad situations.
Using what we already know. A good starting point.
Essential first step. Gives you a baseline. But especially with new tech and clever attackers, it's just not enough by itself. You need more.
So what's the second phase?
That's the creative phase.
Yeah.
This is where you need multidisciplinary teams really thinking outside the box,
Yeah.
using divergent thinking, imagination, to probe for the truly novel, the unforeseen hazards and vulnerabilities.
Trying to anticipate the unknown unknowns, as they say.
That's a good way to put it. It complements the empirical approach by looking beyond past experience.
Okay, but even with these phases, are our current best practices keeping up? You hear about systems still being vulnerable.
That's a fair point.
Right.
Many current standards and practices, while valuable, can still be very manual, hugely resource-intensive, costly.
And maybe not focused enough?
Often, yes. They might lack sharp risk-based prioritization, and crucially, they can struggle to keep pace with how fast technology and the threats are evolving.
So we need something smarter.
Exactly. This is pushing towards ideas like Smart Safety Assessment, or SSA. Imagine a system that helps continuously evaluate risk, focusing resources automatically on the most critical areas, like having a constant, intelligent audit running.
Okay, continuous focus assessment. And linking this back to security, how do we make sure we're looking at the whole picture, not just the tech?
Great question. You absolutely need a holistic view. Security isn't just about firewalls and encryption. This leads us to something called the CoPS framework.
CoPS, what does that stand for?
It helps consider vulnerabilities across 3 interconnected contexts. C is for cyber system.
Communications, data, the digital side.
Right. O is for organizational and governance. That's people, procedures, the supply chain, even the company culture. Big area.
Often overlooked, maybe.
Very often. And P is for physical. Infrastructure, the actual facilities, the machinery itself.
Cyber, organizational, physical, COPS.
Exactly. This integrated framework is vital because it forces you to look at the overlaps, the synergies. Attackers often exploit weaknesses that cross these boundaries.
Makes sense. A weak procedure in the organizational part could let someone exploit a cyber vulnerability to affect the physical train.
Precisely. And we're seeing this recognized more formally. European railways, for instance, are bringing in new regulations. There's a big emphasis now on security-informed safety cases.
Meaning you can't really talk about safety properly anymore without deeply considering security. They're intertwined.
Absolutely intertwined. Which brings us neatly to the path forward. It's about the synergy you get from truly integrating safety and security assurance. Doing them together.
Not just side by side, but woven together.
Yes, it's not just tidier. It leads to much more effective, more efficient results. It gives you a systematic framework for managing the total risk.
Okay, so for someone listening, maybe an engineering student, someone starting their career, or just a railway enthusiast, what's the core takeaway? How does this integrated framework actually look?
Well, it rests on about 7 fundamental principles. Think of them as the pillars supporting this whole approach to total risk management.
7 principles. Okay, let's break them down. What's number 1?
Number 1, prediction and proactivity. This is about planning ahead, identifying stakeholders, collecting data, assessing risks before you even start designing in detail or before threats materialize. Beating that human tendency to only react after something bad happens.
Right, getting ahead of the curve. Principle 2.
Prevention. These are the actual measures you put in place to eliminate risks, or at least reduce the likelihood of a threat succeeding or a hazard occurring, building in the defenses.
Okay, proactivity, prevention. 3rd.
Containment and protection. If something does go wrong, an accident or a security breach, these are the actions aimed at limiting the damage, reducing the severity of the outcome. Damage control.
Got it. 4th principle.
Preparedness and response. This is about having solid plans and the right resources ready before an incident. How do you manage failures, degraded modes, emergencies? You need to have practiced it.
Plan for the worst, hope for the best.
Okay, number 5, recovery and restoration. After a disruption, how do you get back to normal service quickly and safely? These are the measures to minimize downtime and restore full function. Getting things back on track, literally.
Makes sense. Principle 6.
This one's crucial. Organization and learning. How are your teams structured? What training do they have? Are people competent? And critically, are you actually learning from incidents and near misses and feeding those lessons back into the system?
Closing the loop. So history doesn't repeat itself.
Exactly. And the final principle, number 7.
Continual enhancement. This is about never standing still. Setting performance targets, measuring how you're doing, auditing your processes, and constantly looking for ways to improve, because the threats and the technology never stop evolving.
So prediction, prevention, containment, preparedness, recovery, organization, learning, and continual enhancement.
Those 7 applied together systematically.
Yes. They underpin how you attain, maintain, and improve overall safety and security in these really complex systems, like railways. Understanding these gives you, the listener, a really robust framework, whether you're studying this, working in it, or just fascinated by it.
So next time you see a train speeding past, maybe give a thought to all that complexity. And here's something to ponder. As we integrate even more cutting-edge, tech-thick, advanced AI, maybe even quantum computing down the line, what new, totally unforeseen challenges might pop up? And how on earth will we assure safety and security then?
That's the multi-billion-dollar question for the future, isn't it?
Yeah.
Definitely something to think about.